sentences or paragraphs if you want. An absolute max or min be at the end of an interval, closed interval. An absolute max or min be at the end of a closed interval. Anyone? Don't be afraid to be wrong. That's what we are discussing here.
Is it max?
So an absolute max or min be at the...
Cannot be? Oh, sorry.
Say it again.
I was just saying cannot be. Is it cannot or is it can be?
Aha, let's take a look here. So can or cannot be at the end of the interval?
Can.
Very good. Good. A function cross a horizontal asymptote.
Can.
Yes, of course. We had an example. We didn't graph a function like that, but we had an example in which I said, okay, the function can do this. Here it is. It crosses the horizontal asymptote. Perfect. A function cross a vertical asymptote.
Can.
Cannot. So if a vertical asymptote is this, remember the function either goes to infinity or goes to negative infinity, or both to infinity, both to negative infinity, or vice versa. It can never cross here because it's undefined. Here, who cares? The horizontal asymptote is basically this piece and this piece. But I cannot graph a line by showing you this end and this end. I have to show you the whole graph. So then the function can cross the horizontal asymptote. But it can never cross the vertical asymptote because at that point the function is undefined. Awesome. Final sentence here. A local max min be at the end of a closed interval.
Cannot.
Yes. A local cannot because the function does not exist on this side. Remember, for the local, I have to be able to show that the function exists on both sides, and this is the maximum, local maximum, as long as all the other points are smaller. The height is lower. So a local interval, a local max or min, has to have this interval. If I cannot have this interval because the function doesn't exist on this side, this cannot be a local. Awesome. Well done. Any questions? The only thing that I did not get the chance to talk about, and I would like to leave it at the end, I don't know when, it's the slant asymptote. I did not show an example. I will not test you on the slant asymptotes, but I just would like to mention or just show an example without going through the steps. So we know that a horizontal asymptote is a horizontal line where the function eventually goes to, right? Both sides or one or the other. We know that the vertical asymptote is a vertical line where the function is undefined. But what is a slant asymptote? Well, slant means oblique. It means not horizontal, it means not vertical. It means something like this or something like this, but it has to be a line. A line, vertical line is the vertical asymptote, a horizontal line is the horizontal asymptote, and something like this will be a slant or oblique asymptote. So let me just show you an example like that right here. So let's suppose we have a vertical asymptote here. Let's say we have the slant asymptote this. So this is a slant asymptote. And now I'm going to graph a function. So here's one option. Just for you to have an idea what a slant asymptote is. I will not test you on this. But I want you to know that there are three asymptotes. Not just the horizontal and the vertical, but also something called oblique or slant. Okay? So, of course, at infinity, the function has, at negative infinity, the function has to approach the slant asymptote. When x approaches infinity, the function also has to approach at the other end of the asymptote, like it does here for the vertical. This was all discussed in 137. But since here we have a lot of more work to look at, this is, in my opinion, not super important. We can go through a step-by-step procedure, but I think that this is what we have already is good enough. Now, one comment I want to make. A function can cross a horizontal asymptote as well as slant. So a function can do something like this. Can cross the slant, can cross the horizontal, but it will never cross the vertical. And one last comment that I would like you to remember. If a function has a horizontal asymptote, cannot, we're talking about rational functions. If a rational function has a horizontal asymptote, cannot have a slant asymptote, and vice versa. So if the function has a horizontal, don't look for a slant. If the function has a slant, don't look for a horizontal. And some time ago we said degree n over degree n. What is the horizontal asymptote here? Degree n, degree greater than n. What is the horizontal asymptote here? And there is only one type for slant, one type, exactly one. Degree is n plus 1, and here's degree is n. And this, no horizontal, but slant. So a slant asymptote exists only if the numerator has degree 3 and the denominator degree 2. Or the numerator degree 10 and the denominator degree 9. Or the numerator degree 2 and the denominator degree 1. The numerator has one more unit in its degree. But can anyone give us the horizontal asymptotes for these two?
Second one is 0. And
The second one is 0. Very good. And this
the first one is like, let's say, like whatever the
leading coefficient over the leading coefficient. Awesome. Thank you.
Yeah.
Who was that? Tariq, thank you. Yeah. So same degree is the leading coefficient over the leading coefficient. Higher degree in the denominator always is 0. And if this is, and we're not going to do this, and if we, sorry, I have to mute you. If this is degree 2, this must be degree 3 for slant. As you see, there are 3 different situations, completely different. Okay, that's it. So now I would like to continue with 3.5. 3.5 is more applications. And specifically, again, a max-min called optimization. So from the beginning of chapter 3, that's all we talked about. Max min, first derivative, and then graphing with the help of the second derivative. That's all we did. Okay, so always stop me if you have questions, you know that, please. Okay, so I already have this, the book ready here. Okay, so let's start by looking at, let's look at two problems. We'll choose whatever you want. What I'd like to work on is something like, for example, minimizing the surface area, so we can talk about this. Also maximizing profit. And I think that that could be enough, unless you want to look at more. Is that okay with everyone?
Yes.
Okay, thank you, Sandley. So 23 then. And this is what page? 329. So let's read it. Minimizing surface area. Every time you see minimizing, maximizing, you have to think of the first derivative, critical numbers, and study the sign. Okay, open air waste management is designing a rectangular construction dumpster that will be twice as long as it is wide. Stop. So here is, if this is the width, I'm going to call it X, but this is the length. What will I call it?
Y.
Let's read it again. Open air waste management is designing a rectangular construction dumpster that will be twice as long as it is wide. So if the width is X,
2x.
very good. Twice as X. Is that clear for everyone? Thank you, Tariq. Okay.
Yeah.
Perfect. Good. So let's share again. And must hold 12 cubic yards of debris. What does that mean? What is 12 cubic yards of debris? Easy to guess because it says cubic yards. What do we measure in cubic yards?
Is it by feet?
But we don't have feet, we have yards. But what do we measure in cubic yards?
Volume.
Very good. So the volume of this container, thank you, Levi. So the volume of this container has to be 12 cubic yards. So for now, what do we know? First piece of information, the width is X, the length is 2X. Second piece of information, they're telling us the volume must be 12 cubic yards. Okay, let's see what else they want. So we establish what is given so far. Find the dimensions. In other words, length, width, height. Find the dimensions that will minimize its surface area. So the question is, find length, width, height to minimize the, go back, right? It says minimize the surface area. Minimize surface area. So we are asked to find these dimensions that specifically give us a minimum surface area. Where is our starting point? Where do I start? It's okay if you're wrong, just say something. You can say, let's start from
From 2x to x.
okay. And what do I do with this?
Set it equal to 12 yards.
So that's your first point. Okay, that's fine. So we want to build the volume. So the volume of a rectangular box is area of the base times the height.
It would be x times
To
12.
x. No, we don't have that yet.
Oh,
First, we are discussing the volume. So the volume is length times width times height. Now we set the volume equal to 12. So 2x squared times h equals 12. So we have this equation. I will simplify it. What can I simplify it by immediately? I can do that.
Divide by 2.
Awesome, excellent. So I have my first equation. That was my starting point. That's fine. Good. What is the next step? So I have obtained an equation from the given information from 1 and 2. Combining them, I obtain this. Awesome. Where's my next step? Remember what we are trying to do. We have to minimize the surface area. Where will be my next step?
Do you find the derivatives?
I can't. I have to find the derivative of a surface area, but I don't have the function yet. I'm not asked to minimize this. This is not the surface area. I'm asked to find the surface area and then minimize it.